So every circuit is composed of components that supply energy, which is supplied to many charges, so the energy per charge is voltage. And in addition to components that supply voltage, there are components that use up the energy or dissipate the voltage. And then there are the wires, which we assume are ideal, and that means that they don't dissipate any voltage, and obviously they don't supply any voltage as well. In any circuit, the amount of voltage that is supplied equals the amount of voltage that is dissipated. This is another way of expressing the law of conservation of energy. Right? The amount of energy supplied equals the amount of energy that is dissipated. Resistors dissipate potential energy. Right? That's an example of some components that dissipate energy. And then next we'll see examples of components that supply energy. So resistors, they dissipate potential energy. And an electron that moves through a resistor feels a drop in its potential energy. And for this reason, we call the voltage across a resistor a voltage drop. Components that supply voltage are called power sources or just EMF sources or just sources sometimes. And these include things like batteries, cells, generators, and power supplies that you plug into a wall. Now, we've talked about what components supply voltage and what components dissipate voltage, but we haven't talked about where the energy goes. So components like resistors, they convert the potential energy into heat. So the voltage is dissipated as heat. And for something like a filament in a light bulb, the potential energy is not only converted into heat, but it also is converted into light. Batteries, where do they generate? How do they generate their energy, their voltage? Well, they use chemical energy. That's what a battery does. It uses chemical mechanisms to separate charges to the two ends of the terminal, and it maintains a constant charge separation, a constant voltage across the terminals, and it uses chemical energy and chemical reactions to do that. Other things like generators can generate voltage using mechanical means, and we'll study those later. Oops. So I threw around the word EMF source earlier, so we better understand what an EMF really is. EMF stands for electromotive force, and it's given the variable epsilon, and it's defined as these three different things. These are three separate definitions, which you must know, and they're all perfectly suitable definitions. But they define EMF in different terms, so we have to be familiar with all of these. The first definition of EMF, electromotive force, is it's the energy per unit charge made available by the source of some circuit. Okay? And I'm going to skip the second for now and come to the third. The third definition is EMF is the work done per unit charge in moving charge completely around the circuit. So the first thing that we notice, energy per charge, work done per charge. These are the two definitions, these are similar definitions to the definition of voltage or potential difference. Okay? EMF is essentially the total voltage which is made available by some source of a circuit. So it could be the total voltage made available by a battery or by a generator or any other source, any other EMF source. And the third definition, which is in the middle here, which I skipped and I'll now come back to, the third definition is it's the power supplied per unit current to a circuit. So you can think of it as delta E over Q, energy per charge, or work per charge, or power per current. Now, this is the way, these are three definitions to know. Here at the bottom is how I like to think about it. It's the total voltage provided by the power source. So it's a number. EMF is a value, like 15 volts, and it's measured in volts. Now here's the thing about EMF sources. EMF sources supply most of their EMF to the rest of the circuit that they're connected to. But real EMF sources use up some of their own energy because of internal resistance. So voltage is dissipated whenever we have resistance. And EMF sources have internal resistance, which causes them to use up some of that EMF which they supply use it up internally before it even is before it's made available to the rest of the circuit. So here's the way we define internal resistance, or the way we think about it. And this is a great thing to be able to recite for IB test questions. Internal resistance is the resistance inside an EMF source, which decreases the voltage supplied to the rest of the circuit whenever a current runs through the EMF source. And we're going to talk about that last bit shortly. So the basic idea is this. Part of the EMF is dissipated by the rest of the circuit. So everywhere here that I say the circuit, it really means the rest of the circuit. That's shorthand. Part of the EMF is dissipated by the rest of the circuit, and part is dissipated by the EMF source itself. The total energy or voltage supplied, we said earlier, is always equal to the total energy or voltage dissipated, right? And we could write that in an equation like this. But the total voltage supplied is called the EMF. That's what I've just told you. And on the right side, the total dissipated voltage is equal to the voltage used by the rest of the circuit plus the voltage used by the EMF source. And of course, the EMF source is part of the circuit. So when I say circuit again, I mean the rest of the circuit besides the EMF source. So this would include the voltage dissipated by resistors, by filaments, and any other, components connected to the EMF source. So the voltage dissipated by the circuit is equal to I times the equivalent resistance. Right? That's how much voltage is dissipated by everything that the EMF source is connected to. The voltage dissipated by the EMF source is I times little r, where little r stands for the internal resistance. So if you plug this in right over here, IREQ, and in place of V used by the EMF source, plug in I little r, you get this equation right here. And that is an important equation, so we box it. And if you solve for the current, right, it's a simple exercise to solve for current, isolate current, and that gives this equation over here. So we use those in solving problems. And here's a problem, speaking of problems. Let's say you measure the voltage across a battery's terminals when it's not connected to anything, and the reading you get is 12 volts. Right? So there's no current running through the battery at that point, which means, look at this equation, the last bullet. Right? If the current is 0, then there is no voltage dissipated by the EMF source. So when you measure across the terminals of a battery and there's no current, right? When you take that measurement, the voltage which is dissipated by the EMF source is 0, and the reading you get is the total EMF. So 12 volts is the total EMF. Okay, we've got that number. We then connect a motor to the battery, and we measure a voltage across the terminals of 10 volts. So when we send a current through that EMF source, through the battery, it's internally dissipating 2 volts out of the 12. So because there's a current running through it now, right, because there's some I, when you multiply the value of I times R, the amount of voltage which is being dissipated by the EMF source is 2. The power rating of the motor is 8 watts. What is the internal resistance of the battery? Well, we're going to use this equation. The EMF is equal to the voltage, the total voltage used, which is the voltage used by the rest of the circuit plus the voltage used by the EMF source. And of course, the rest of the circuit merely is composed of the motor. So this we could rewrite as the voltage used by the motor, since there's no other component connected to this circuit. And of course, we know the voltage used by the motor is 10 volts, because when you connect the motor, right, you measure 10 volts as the potential difference across the terminals, which means the motor is using up 10 volts. It's dissipating the full amount supplied from the terminals, which is 10 volts. And on the right side, we could break the voltage used by the EMF source into I times R using Ohm's law, right? And we know that the current through the EMF source is equal to the current through the motor, since all of the current is passing straight from one terminal through the motor and then back to the other terminal. And of course, current, right? Well, we know that power is equal to I times V, current times voltage. So if you solve for current, you get power over voltage, and you can plug in those values, 8 watts, 10 volts, and it's a simple exercise from here to solve for R. R comes to, let's see, what is this? 2 volts times 5/4. That would be 2.5 ohms is the value of R. We use special devices to measure current and voltage. Right? So in this example, it says you measure the voltage. Well, how do you measure the voltage? We use things called ammeters and voltmeters. So whenever we want to measure current, we use an ammeter. And whenever we want to measure voltage, we use a voltmeter. Clever names, right? Because amperes are the unit of current and volts are the unit of voltage. Now each device is it operates by connecting to a circuit and then drawing some current through that device. So you connect an ammeter and then current passes through the ammeter, or you connect a voltmeter and then current from the circuit passes through the voltmeter. And both of these devices operate by measuring how much current is flowing through itself. So the voltmeter measures the current running through the voltmeter, and the ammeter has current running through it, and it measures how much current is running through it. So we use ammeters to measure current, right, through a resistor or any other component. And the way it works is we connect an ammeter in series with the resistor or component whose current we want to measure. So if you want to know what's the current through the third resistor of this circuit, you just connect that ammeter in series with R3 and you read the value. Now because they're in series, our resistor that we're measuring the current through, it's in series with our ammeter. And that means that all of the current passing through the resistor also passes through the ammeter, because there's only one path if they're connected in series. And so all of the current flows through a single path, right? And it flows through the resistor first and then the ammeter second, or it could flow through the ammeter first and the resistor second. So here's how we write that. The ammeter then measures the current running through it. It measures its own current, and it displays this value as the current through the resistor. And that's how it works. Real simple. Voltmeters. We use these to measure voltage across a resistor or any other component. And the way we do it is, instead of connecting it in series, we connect a voltmeter in parallel with the resistor. Right? So when we connect in parallel, we know that whatever voltage drop there is across the voltmeter is equal to the voltage drop across the resistor that we're measuring. So here's how we write that. Using Ohm's law, we know this. Right? V equals IR for the voltmeter. So the voltmeter measures its own current, just like the ammeter, but then it takes that value of I and it multiplies by its known pre-programmed manufactured value of resistance. So every voltmeter has some manufactured resistance value, and the voltmeter knows what its resistance value is. It's programmed into the voltmeter, and every time that voltmeter takes a reading of current, it then multiplies the current by its own value of R to arrive at the voltage. Right, so the resulting voltage, which is this value, it's displayed as the voltage across the resistor, since that is equal to the voltage across the resistor, because they're in parallel. And that's how voltmeters work. So the problem with ammeters and voltmeters is that whenever we connect them to part of a circuit, it's like we've added in another resistor, and that changes the circuit. So the readings that you get won't necessarily be accurate of the true current through the resistor or the true voltage, because we've altered the circuit. So here's the problem with ammeters. When we connect them, they dissipate some of the supply voltage, and that means there's less voltage to be dissipated by the resistor that we're measuring. So if you reduce the voltage across the resistor, right, if you reduce the voltage drop, V equals IR, and now you've taken away some of the current. So the reading that you get from the ammeter for current is smaller than it really would be if there were no ammeter in the first place. So to fix this, we build ammeters to have near zero resistance. And yes, that way, they dissipate virtually none of the supplied voltage. And that keeps our readings nice and